Let's move on. Let's talk about some more examples of recursion. And we saw one example last time, which is recursion, where you use recursion in two parameters. We looked at a function called take. Let me look at another function which is maybe a little bit simpler in some ways, but actually really useful. It's a standard function called zip. Okay? So let me show you an example of what zip does. Zip takes two lists. Imagine that's one list. Imagine that's the other list. And it creates one list out of these two lists, not by joining them together, but by taking them pairwise and making a pair of the first elements, a pair of the second element, pair of the third element, and so on. Okay? Can you see why it's called zip? So if I zip, sorry, don't want photos. If I zip the list from 1 to 10 with 100 to 200, so I've got a zip now with one half is longer than the other, but it'll ignore the bits that it can't use. And so we pair up 1 with 100, 2 with 101, and so on. Now zip works not just for lists of numbers, but lists of any two types. So I could zip with a list of characters, for example. How do I write a list of characters? Well, that's the same as a string. So I can write it using this notation. And so now I've formed a list of the numbers together with the characters in this list. And you notice that if one of the lists is too long, we'll ignore the elements that are there if there are too many. And if we zip an empty list together with something, we just get the empty list. And it doesn't matter which one of them is empty. Any questions?
What is the type of the list? They're not lists, right?
So zip gives you a list as a result, but each element in the list is a pair. Okay, so we talked a little bit about pairs in the quiz that we had last week. So pairs are a way of grouping things which have where there's a fixed number of things. Here, the groups have a fixed number, 2 things, but where the types of the things in the group can all be different. That's very different from a list, where the types of the things in a list all have to be the same. So here we've grouped a number and a character. So we could say that this is a tuple of an int and a char. But the type of zip, in general, it takes a list of anything you like and another list of anything you like, which doesn't have to be the same as the first list. For example, the first one might be numbers, the second one might be characters, and produces a list of pairs of things with the first and the second list. For example, a number and a character. So this is another example of a polymorphic type, a function that has, in some sense, multiple types. Can be used in multiple ways. So let's give a definition of zip. And I'm calling it zip prime because it's one of the standard functions available to you in the prelude. You don't have to load it from any module. It's accessible. Okay? So what's the base case? What do the parameters of the base case look like? Somebody?
You have the first parameter could be an empty list, and the second could also be an empty list, but in another. Oh yeah, both of them could be empty lists.
Yeah, that's a perfectly good base case. but it's not quite as general as we might like. If the first list is empty, it actually doesn't matter what the second list is, right? Because if you try and zip an empty list with something, this example down here, then you get the empty list. So actually it doesn't matter what the second one is. If the first one is empty, the answer is empty. And similarly, if the second one is empty, it doesn't matter what the first one is. The answer will also be empty. So we have two base cases, namely when either of the two lists is empty. Okay? Now, immediately when I talked about base case, you probably guessed that I'm going to try and define this using recursion. Okay, I should have said that. Okay? So what do the non-base cases look like? Well, the first list can't be empty, and the second list can't be empty. So both of the lists are non-empty. What do non-empty lists look like? Well, they all look the same. We can write a pattern that will only match non-empty lists. And that is if the first list has the shape A followed by A's, and the second list has the shape B followed by some B's. So that's the recursive case. Okay. So this is going to be recursion in two parameters. We're going to solve the problem of zipping together these two bigger lists in terms of the process of zipping together the two smaller lists, A's and B's. Okay? So this is what I mean by recursion in two parameters. We're making both of these parameters smaller at the same time. And why is that? Well, because that's the way that zip works. It works in the two lists in synchrony, kind of aligned. It lines up the lists, takes the first two elements and the second two, and so on. So you have to ask yourself, if I know what the result of this is, how would I build the thing that I want, which is the result for this thing? Well, this is missing one element. That element is the pair that we build by putting together A with B. So we take the pair A, comma B, and we put it on the front of the result of zipping the rest of the list. So when you want to do up a zip, you have to kind of go past the first notch, zipping the first two teeth, and then zip the rest. So zipping in that sense is a recursive process. Until we get to the base case when one half of the zip has run out. We can't push the zip any further, and that's these cases. So somebody gave me a nice observation in the break. In this definition of zip, I took the base cases first and then the recursion case. There's nothing that says we have to do it in that order. Actually, if you do it in a different order, you can make the definition slightly shorter. So let me just comment out the first two lines. Let's imagine we define this case, the recursive case, first. So the only case where we don't match this is where either the first list is empty or the second list is empty, or maybe both. But it doesn't matter. All of those cases give the same answer, which is the empty list. So if we reorder this to put this equation first, then the second equation can be, I don't care what that list is, I don't care what that list is, because the answer must be the empty list, because one of these two guys must be the empty list. So that's an alternative and actually neater way of writing it than the way I did it with this order. So thanks for that observation. Any questions? Now, can we define zip with a list comprehension? Because I said, yeah, let's not just do everything with recursion. Let's try and, make use of all the tools we have. So here's a first attempt that you might think. Zip. I've got two lists to zip together, and I'm going to build it with a list comprehension. And I'm going to use those two lists as generators. I'm going to take, let's call them A's and B's to make it look like the previous definition, rather than X and Y's. Let's take values A from the list A's and values B from the list B's and build the list of pairs A, comma, B. What do you think? Will that zip them together? Taking the A's from one list and the B's from the other. We're building pairs A, B. Thumbs up? Thumbs down? Will that work for empty lists was the question. Yeah, list comprehensions work fine for empty lists. If you have no generator, if the generators are empty, you get empty. If one of these generators is empty, you get empty. No problem there. Well, let's try it. Well, no, let's not try that. That'd be boring, wouldn't it? Let's write a property. If we have two lists, X's and Y's, and we want to zip them together, we want the zip function, the standard one, should give us the same result as so we've used what we know is a correct solution. That's the thing we're actually trying to build to check whether they're the same. Might be a good idea to write the types because we don't want the zip to use lists of unit, those blobs that we saw in the last lecture. So let's do, I don't know, lists of int maybe. They're nice to print out. And it's a bool. Okay, let's quick check that. It failed very quickly. That's the counterexample. So they're the two values for this X's and Y's for which it fails. So what would you expect if you zip those together? You zip a list with one thing in and a list with two things in. How many things will the result list? How many elements will the resulting list have? Resulting list will have just one element, and that thing will be a pair of the first guy in this list and the first guy in this list. There it is. We can just check that our other zip function also does that. But zip double prime, and you should have spotted this from lab 1, because lab 1 you need to build all the coordinates of a chessboard. Maybe you haven't done that yet. It's too many things. What happens when you use a list comprehension with two generators is we're not zipping, we're taking all combinations of these guys and these guys. Right? So you're going to get a quadratic, you're going to get sort of n squared. Or rather, if there are m guys in this one and n in this list, you're going to get m times n results. Okay? So when you use a list comprehension, it does something quite different to zip. That's why zip is actually so useful. Because you can't do that so easily with list comprehensions. In fact, I can't think of an obvious way of writing zip using a list comprehension. However, once we've got zip, together with list comprehensions, we can actually do loads of fun stuff. So we'll see some more examples of that shortly. Any questions? All right. Let's take another example where we do recursion over two parameters, but where those parameters are a number and a list. It's this function bang bang, which I think I would pronounce index or index. Let me show you what it does. It's an operator. It's a function written with symbols, and when you use it in between its two arguments, like you do with plus, times, and so on. So let's take an example of the numbers from 1 to 10, and I want to take the number at index position 1. So that's what that says. Give me the number at index position 1, and that's 2. let's deal with a different example. Let's use a string. Give me the character at index position 1. That's the character E. So that means the character at index position 0 will be H. Okay, so that's what the function does when it's well behaved. What about the corner cases, the extreme cases? What happens when we try and take something below 0? Is there a sensible answer? There's no empty character, right? There's no such thing as an empty character. Yeah?
Does it go the other way?
What lives over there?
No, it starts from the right instead. So
It starts from the right and comes from the end. Yeah, it could do. That would make some sense. That if you have a negative number, it means index from the back. That's quite an interesting one. I'll remember that for a possible exam question. Thank you very much. But it doesn't actually do that. What it actually does is give you an error. Okay? So this is what you call a partial function in mathematical terms. It's not defined everywhere. So when an error is really not an answer, what we say is the function is not defined when we have a negative number. What about if the number is bigger than the end of the list? If it falls off the end of the list. So instead of 1, let's suppose we have 20. Obviously, we don't have 20 characters in this, 21 characters in this list. We also get an error. The error message is different. It's informative, but that's really just to help us debug programs. If we get an error, our program is broken. We've got a bug to find. So the fact that we get one error message or another doesn't really say so much. We can't use that for anything useful other than helping us debug our program. So this is a function that can go wrong. Question?
No.
No. Okay. So it's a little bit different from zip. Zip was a robust function. It doesn't go wrong just because you give it one list shorter than the other, but the indexing function does. So let's define it. Since it's a partial function, we're going to use recursion, but since it's a partial function, we have to think in terms of not only base case and recursive case, but also error case. So maybe it's easier to write down the error cases first. I'm going to write it as, I'm going to call it bang, bang, bang. So the error cases are when the list is empty. If you have an empty list, you must always have an error because there's no element you can return from an empty list. So there's no choice but to give an error. So I'm going to call it bang, bang, bang. And it doesn't matter what I give it as first argument, that thing will give us an error. So that's an error case. What message does it normally give? It doesn't matter what message we give, but let's try and mimic the real function. If we give it the empty list and ask for something at index 0, that's the first thing in the list, it says the index is too large. So no index is small enough for the empty list. Even if we give it -1, oops, sorry, brackets around -1. Otherwise it thinks I'm subtracting 1 from an operator. That wouldn't work. Okay, negative index. So actually the first case is a negative index. Okay. Anyway, this is index too big. The other case was it doesn't matter what we have as the first argument. If the second argument is some number where the number is less than 0, then we also get an error. Negative index. Let me just write that on a new line. Okay, so this is looking a bit messy because this is an infix function. So it's a bit hard to read. I can see that. Never mind, we'll get the hang of it. Okay, so that's the error cases, but what about the base case? What's the base case? What's the simplest non-error case that you can have? Well, the list has to be non-empty, right? We'd agree on that. Because if the list is empty, it's got to be an error. So it's a non-empty list, x on the front of something x is. And what element are we going to take from that? What's the easiest case?
0.
The index number 0. Thank you. So we can write that with pattern matching, if we will. You don't have to, but we can. So we're taking 0 from a non-empty list, then the answer is x. That's the guy. So the other case then, the final case, is a non-empty list. All right. I'm too close to the side of this chair, so I can't type properly. A non-empty list and a number, and a number n, which must be no smaller than, it can't be less than 0, and it can't be equal to 0, so we know that n is bigger than 0. So what we do is recursively throw away the first element and look for element with index number n minus 1 from the rest of the list. If you want the second element of a list 1, 2, 3, that's the same as the first element of the list 2, 3, which is the same as the 0th element of the list with just a 3 in it. Okay, so that's the way the recursion works. In each step of the recursion, both the list and the number get smaller. So again, it's another example of recursion in 2 parameters. Any questions? Okay, before you take a break, let me send you away with a puzzle. Can you define the indexing operator using list comprehensions? Okay, let's get back to where the puzzle we had. The index question. Can you define index using list comprehensions? What do you think? Anybody got any ideas? How you might do it? Yep.
You can't, because list comprehensions necessarily return lists.
That's true. So the answer was technically correct. The list comprehension returns a list. So you can't use a list comprehension if you're trying to produce a value. While that's technically true, it's not quite in the spirit of the question. So I guess what I meant was, can we define it with the help of a list comprehension and know without having to define any recursive functions? So if I rephrase it that way, can I define it where the list comprehension does most of the work? Let's put it that way, yeah.
You can do it using zip with an infinite list of numbers and compare with.
Nice, okay. So the answer is yes, we can do it by zipping with an infinite list of numbers, blah, blah, blah. We'll get to that. So let's do exactly that. So the trick is we can use zip, and the way we're going to use zip is to index things. We already saw an example of that. Let me scroll up. There it is. Oh, no, it isn't. Zip somewhere. Sure, I've got a zip. There it is. So this was an example where we took a list of numbers and zipped it with a string. And what we got is we're indexing the characters in that string, characters in that list. So if we actually index from 0 instead, we'll be indexing in the right way. So now we've got a list of indexed things, and we're looking for the thing at a certain index. So we can use a generator in the list comprehension to generate this list. And we can use a guard in the list comprehension to throw everything away except for the element that has the right index. So if I'm looking for the index number 2, I'll make sure I keep this one from this list, but nothing else. Okay, so let me try and write that down. I'm going to define should we give it a name? Let's call it index. Index, some number and some list. I'm going to use a list comprehension that I'm going to build by zipping numbers starting with 0 up to something or other with the list x's. So what something or other should I put here? How many numbers do I need to index all of these things? Well, it's roughly the length minus 1, in fact. Length minus 1. But actually, I don't actually need a number here. I can use this expression, which is a perfectly valid list in Haskell. And it's the infinite list, starting with 0. We'll starting to get slow, so let me just interrupt that. So the thing about list zipping is, if one of the sides of the zip is too long, it doesn't matter. We ignore the stuff we don't need. That's one fact. Fact number 2 is, Haskell is a lazy language. So it's not going to build an infinite list until it knows you really need it. And you're only going to need the first chunk of it. So it's not going to build more than it needs. So this is a way of indexing all the values in this list. And let's call those things, let's give them a name. Let's call them, they're pairs, so we can use pattern matching. The first component is the index, and the second component is the value. So if we start by this definition, then that's the same as zipping. So this is not the complete definition yet. It doesn't even have the right type. But let's index the 10th element of the numbers from 100 to 200. And what it does is generate all the pairs of the index and the value. So what we're doing is ignoring this. We're not using n yet. We've just built this list of things. So what we want to do now is, in fact, we don't want the whole list of these things. What we're interested in, we're only interested in indexes. Okay? We're only interested in values. But which values? We want the values where the index I is equal to the number n that we provided as a parameter. So if we're asking for index number 7, we only want the values of v where its index is equal to 7. So we use a guard for that. And we're saying we're looking for the indexes I, which are equal to the parameter n. So we're taking all the pairs of values, index and value, but we're throwing them all away except for the one where the index is equal to n, the thing we're looking for. And what we build is the list containing just that value. Not the index, the value. Okay? So this thing now returns something quite close to what we're looking for. Let's try the 10th element of this. What does it give us? Well, it does give us sort of the right thing, except that it's in a list. So how do we get rid of that list? Well, we want the first element of this list. We want the head of this. So that's a bit of a puzzle. It may take you a little while to get your head around it because it's using all the features of list comprehension, in other words, generators and guards. It's also using something we haven't seen much of. We're actually doing pattern matching here. Not essential we use pattern matching. We could use the little selection functions first and second, but it's neater to use pattern matching. Is it correct? Well, let's try it. Let's try. Okay, I'll leave. If I try it now, I think I'm going to run out of time. So I won't do a quick check property. You might think about how you want to do a quick check property for this. The thing you have to think about when you do a quick check is that if you have a function like this one, a partial function, a function that might give an error, you better make sure your quick check tests don't give errors, because errors are the same thing as going as a failed test. Okay? So you have to make sure the property you test is a property that will always work, which means that you can't have an empty list and you can't have a number which is outside the indexes of the list from 0 up to length -1. So you might want to think about how you could define a quick check property for testing that this function behaves the same as the standard function, which is written like this, and whose type is give me a list of anything you like and an index, and I'll give you a value that's found at that index, or give you an error maybe. Any questions?